Testing, testing. Okay. Testing, testing. Okay. Okay, let's get started. My name is Michael Dix, and these are the 2014 AP Calculus AB and BC questions. These are the free response questions that are available for free from the College Board AP Central website. So if you want to follow along, you can download those there. I'm going to work through these as if I am a student, so I'm going to reason through them, hopefully using the same language that you would use when you see these problems. So here we go. I'm going to do the 6 AB problems first, and then at the end I'll do the 3 BC problems that were different. So in 2014, number 1 was an AB and a BC problem. The averages are on the top left-hand side of the screen there. The AB average for this problem was a 2.5 out of 9, and for BC was a 4.26. Let's see what we got on this calculator problem. Grass clippings are placed in a bin where they decompose. For time 0 to 30, the amount of grass clippings remaining in the bin is modeled by A of t, where A of t is measured in pounds and t is measured in days. Part A, find the average rate of change of A of t over the interval from 0 to 30. So when I look at this problem, I notice that the amount of clippings is A of t, and I've been asked to find the average rate of change of A of t. So what they're asking me to do, in essence, is find the slope of A of t. So for part A, I would say the slope would be the function A at 30 minus the function A at 0 divided by 30 minus 0. And in lieu of a graphing calculator, I've got Desmos pulled up here. And so I've got A of x graphed here. You can see it's this decreasing exponential graph. And right here, the slope is negative 0.197. Negative 0.197. And we do want to make sure that we are using proper units. And so if the function A measures grass clippings in pounds and t is measured in days, this would be negative 0.197 pounds per day. Part B, find the value of A prime of 15. Using correct units, interpret the meaning of the value in the context of the problem. So the first part of part B, find A prime of 15. This is something that your calculator could do for you. And this is something you're expected to know how to do in your calculator, is take a function and then evaluate its derivative at a point. And so again, I have my Desmos calculator here. A prime of 15 is negative 0.164. Okay, and again, we want to use correct units whenever possible. So if the function A measures pounds of clippings and time is measured in days, then A prime would be, in, again, pounds per day. So my instructions say interpret the meaning of the value in the context of the problem. So because it's negative, the amount of clippings is decreasing in the bin. And the 15, since time is measured in days, 15 is the 15th day. So I'm going to say on the 15th day, the amount of clippings in the bin is decreasing at a rate of 0.197 pounds per day. Okay. Notice I put a positive 0.197. Oh, I'm sorry, I copied the wrong number. Part B, the answer was 0.164. I used positive 0.164 because the negative in my answer was taken care of by the fact that I said that it was decreasing. Part C says, find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the interval 0 to 30. And so I'm going to set amount of grass clippings in the bin. I'm going to set the function a of t equal to the average amount of grass, which is the average value of a of t. And so in order to do this, the first thing we need to remember is how to find the average value of a function. And so if you're trying to find the average value of a function from 0 to 30, then that will be 1 over 30 minus 0 times the integral from 0 to 30 of my function, which I have here, 1/30 times the integral from 0 to 30 of a of t dt is 2.753. Okay, and the question says, at what time is the amount equal to its average value? So if I set a of t equal to 2.753, and I solve that in my calculator, let's see. If I set a of t equal to this function and solve, I get 12.415. So that's the value of t, that's the time when these two things are equal to each other. And I was asked, find time t. So t equals 12.415. And again, we're going to use units whenever we can. So this is days. Part D says, for t greater than 30, L of t, the linear approximation to A at time 30, is a better model for the amount of grass clippings remaining in the bin. Use L of t to predict the time at which there will be 0.5 pounds of grass clippings remaining in the bin. Show the work that leads to your answer. And so the main idea that we're working with here is linear approximation. And so what we're going to do is we're going to find the tangent line to A of t at time 30, and we're going to use that as our a of t for values of t bigger than 30. So for linear approximation, at 30, that's going to be a of 30 plus a prime of 30 times t minus 30, which, you know, you can calculate these values by hand, but if you're using a calculator, it can also be calculated for you. You can see right here, I've got this blue line right here is the linear approximation. And so if you have this line graphed in your calculator, you want to know where does that line equal the line 0.5. And if I graph both of those together, which is how I would solve this in a calculator, I can find their intersection point is at 35.054. So to make sure I've covered my bases here, I have a correct equation for L of t. And then I can say, if I set L of t equal to 0.5, I get t equals 35.054. Okay, and that's all the work that I would need to get full credit for that. I have an expression for L of t. I'm setting it equal to 0.5 and getting a solution. The calculator is doing the heavy lifting here. This is a calculator active problem. And so we're going to use that to a full effect where we can. Okay, so that is number 1. Number 2, this was an A-B only problem. The average score on this was 3.39 out of 9 points. We've got here, it says, let R be the region enclosed by the graph of f of x equals x to the 4th minus 2.3x cubed plus 4. And the horizontal line y equals 4 as shown in the figure above. Oh, 1 second, let me fix this. correct link posted here. Okay, I'm gonna have a working link posted so people can watch this. Back to the problem at hand. Let R be the region enclosed by the graph of f of x and the horizontal line y equal 4 as shown in the figure above. A, find the volume of the solid generated when R is rotated about the horizontal line y equals -2. So here's my shaded area right here. Y equal -2 would be a line down here. Okay. I'm gonna have a working link posted so people can watch this. Oops. Back to the problem at hand. Let's fix that. Let R be the region enclosed by the graph of f of x and the horizontal line y equal 4 as shown in the figure above. A, find the volume of the solid generated when R is rotated about the horizontal line y equals -2. So here's my shaded area right here. Y equal -2 would be a line down here. Okay. I'm gonna have a working link. There we go. Okay, it's a learning process. We're getting there. Back to it. We are taking this region, we are revolving it around the line y equal -2, and finding the volume of that solid. So what we can see here is that when we revolve this, we're going to have two radii. This is a washer problem. We're going to have big R and we're going to have little r. And the formula for a washer, a volume of a washer problem, is pi times the integral of big R squared minus little r squared dx. This is dx because we are revolving around a horizontal line. And so this problem really boils down to determining what is the short radius and what is the long radius. And if you can find those two values, then you plug them in. And again, this is a calculator active problem, so your calculator is going to do the work for you. Big R, that's the distance between this horizontal line, y equal 4, and this horizontal line, y equal -2. So 4 minus -2 is 6. That is a constant value. And little r is the distance between this polynomial and this horizontal line. And so that's going to be f of x. The distance between them is top minus bottom, f of x minus -2. So we'll call that f of x plus 2. So once I have these values, I'm going to create an integral. I guess I need my bounds still. I need to know where these intersect each other. So let me look at my graph. If I graph these two functions, y equal 4 and this polynomial, I can see they intersect each other at x equals 0 and x equal 2.3. So my bounds are going to be 0 and 2.3. And then when I plug in 6 for big R and f of x plus 2 for little r, I get this integral right here. Pi times the integral from 0 to 2.3 of big R squared minus little r squared is 98.868. Part B, region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Find the volume of this solid. So this is a different kind of volume problem. Here we have right triangles, isosceles right triangles that are standing up in the region R, where the area of an isosceles right triangle is 1/2 base times height, but in this case the base and the height are both the same, so I end up with 1/2 side length squared. So part B, the volume of this slab is going to be the integral from 0 to 2.3 of the area. I'm adding up an infinite number of infinitely thin areas, and so I get the integral of 1/2 s squared dx. And that would be my answer, but I need to know what is s. I need to know specifically what is this distance right here. That's the distance underneath y equals 4, but above my polynomial function. And so in this case, s is 4 minus f of x. Again, the distance between two curves is the top minus the bottom. So 4 minus f of x gives that changing distance s. And when I put it all together, I get the integral of 1/2 times s, 4 minus f of x squared, is 3.574. 3.574. And that's the volume of that slab. Part C, the vertical line x equals k divides R into two regions with equal areas. Write but do not solve an equation involving integral expressions whose solution gives the value of k. So we've got another spin on this problem here, where we're going to take this region R and we're going to use a vertical line to cut it exactly in half. And that vertical line is x equals k. We want to write an equation that would help us solve for k. So basically what we're saying here is that the area from 0 to k has to be equal to the area from k to this other intersection point here, which we know is 2.3. So what I'm going to write is the integral from 0 to k of, how do you find the area between two curves? You do top curve minus bottom curve. So 4 minus f of x has to be equal to the integral from k to 2.3 of 4 minus f of x. And that's really all that needs to be said. This is only true, these two areas are only equal to each other if k is cutting that region perfectly in half. And so that's all we need to write to receive full credit on that one. All right, so that's number 2. Again, the AB average on this was 3.39. Next, number 3, we're now non-calculator problems. This is on the AB and the BC exams, and you can see the averages right there. Just looking at it, if you've done enough of these, you already have an idea of what kind of problem this is going to be. This says the function f is defined on the closed interval from -5 to 4. The graph consists of 3 line segments and is shown in the figure above. So this is the graph of f of x. I like nice big labels for my graphs. That's f of x. Let g be the function defined by g of x equals the integral from -3 to x of f of t dt. So if I'm a student and I'm taking this test and I read this last sentence, the first thing that pops into my head when I see this integral is FTC2. The second fundamental theorem of calculus tells me that I can take the derivative of this, because I have an integral from a constant to a function. So the derivative of this integral is f of x. Is this going to come in handy somewhere on this problem? Probably. I don't know yet, but it probably will. And when I see that, I immediately am drawn to taking its derivative. So part A on this problem says find g of 3. So to find g of 3, I'm going to plug a 3 in to this function right here. So g of 3 would be the integral from -3 to 3 of f of t dt. The integral from -3 to 3, well, that's going to be from this point right here to this point right here. I'm being asked to find the area. And so I'm just going to do that with geometry. What I have here is a triangle with a base of 1, 2, 3, 4, 5 and a height of 1, 2, 3, 4. So that triangle is 1/2 base times height, has an area of 10. And then I have this tiny triangle that has a base of 1 and a height, well, let's see. This value right here looks like -2, but just to be sure, if this is a straight line from this point, 0, 4, to 4, -4, then it has a slope of down 8 over 4, -2. Yeah, so to get from the x-intercept to this point, we went down 2 over 1. So 3 times 2 is 6, divided by 2 is -3. No, I'm sorry, this has a base of 1. Apologies. 1 times 2 is 2, divided by 1 is 1, so that's -1. So the total area from from -3 to 3, 10 minus 1 is 9. Part B, on what open intervals contained in -5 to 4 is the graph of g both increasing and concave down? Give a reason for your answer. So I'll try and squeeze this in up here. Part B, let's start by saying that we know that g is increasing and concave down if g prime is positive and decreasing. And if g prime is positive and decreasing, that tells us g is increasing and concave down. And we happen to know from earlier in the problem that g prime of x equals f of x. And so when I look at the graph of f of x, I'm also looking at g prime. So the question is, where is this graph positive and decreasing? It's going to be right there and right there. So my answer, I have to make sure I phrase this correctly. I'm going to say g of x is positive and, oh, I've already made a mistake. G of x is increasing and concave down on the intervals -5 to -3. That's this one right here. Also from 0 to 2. Because, I need to justify this, because g prime of x, which we know is equal to f of x, is positive and decreasing there. So g of x is increasing and concave down on the intervals -5 to -3 and 0 to 2 because g prime of x, which is equal to f of x, is positive and decreasing there. That's part B. Part C, the function h is defined by h of x equals g of x divided by 5x. Find h prime of 3. So if we come down here, to find h prime of 3, the first thing we'll need to do is find h prime of x. And to find h prime of x, we're going to need to employ the quotient rule because I have two functions being divided here. So the quotient rule, f prime g, the top derivative of the top times the bottom, g prime of x times 5x, minus f g prime, the top times the derivative of the bottom, g of x times 5, over the bottom squared. 5x times 5x is 25x squared. The only change that I would make here is I would make this substitution, g of x, excuse me, g prime of x we know is f of x. So I'm going to say this is equal to 5x f of x minus 5g of x over 25x squared. There's a 5 there that can be factored out, but I'm not particularly interested in that. H prime of 3, this is part C by the way, h prime of 3 then would be 15 f of 3 minus 5 g of 3 over 25 times 9. So I need to know f of 3, I need to know g of 3. How am I going to find f of 3? I'm going to go back to the graph. Go to the graph, find 3, here it is. Hey, we found this value earlier. We already know that this point is 3 comma negative 2. So f of 3 is negative 2. And for g of 3, how do I know g of 3? Well, I found it in part A. So that's nice. Some of the work I already did is coming back to help me. So g of 3 is 9 from part A. Okay, and you could simplify this, but with this being a free response non-calculator problem, I would be content to stop right there. That answer is good enough for me. Part D, last part of this problem, the function p is defined by p of x equals f of x squared minus x. Okay, when you read that, you see functions inside functions. You see layers, you're thinking chain rule. Find the slope of the tangent line, aka derivative. Find the derivative of the graph of p at the point where x is negative 1. Okay, so we need to start part D by establishing what is p prime of x. To take this derivative, hopefully you notice we're going to need the chain rule. The chain rule, we're going to take the derivative of the outside layer first. So f prime of x squared minus x times the derivative of the inside layer, which is 2x minus 1. And we were asked to find p prime of negative 1. P prime of negative 1 would be f prime of negative 1 squared is 1 minus negative 1. So when you plug negative 1 into that, you get 1 minus negative 1, which is 2, times 2 times negative 1, negative 2 minus 1, negative 3. How do I know f prime of 2? Again, go back to the graph. F prime of 2, starting to get a little messy here. 2 is right there, that pink dot, and the slope would be the derivative at that point. So the slope of that line, which forever ago we determined was negative 2, that is the slope at that point. So I've got negative 2 times negative 3, which I think I'll simplify that, is 6. Very popular type of problem where you're making conclusions about increasing, decreasing concavity. I'm surprised this one didn't have anything about a local max or a local min, but that's really common too. This one had some quotient rule and some chain rule instead. Okay. Number 4. Let's see. This was on the AB and the BC exam. We've got the averages there. This one, oh good, a train problem and a table problem. This will be a fan favorite. Train A runs back and forth on an east-west section of railroad track. Train A's velocity in meters per minute is given by a differentiable function v sub a of t, where t is measured in minutes. Selected values for v sub a of t are given in the table above. So we're not given the function, we're given the table for v sub a of t. A, find the average acceleration of train A over the interval 2 to 8. So if what we have is a velocity function, which we do in the table, and we're asked to find average acceleration, they are simply asking for slope. Find the slope from 2 to 8. So negative 120 minus 100 over 8 minus 2. Okay, I don't need to simplify that. If I decide I want to later, I can always come back and simplify, but for now I'm happy with that. What are my units? Let's think about this. Velocity is measured in meters per minute, so acceleration would be meters per square minute. Part B. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time between 5 and 8? Give a reason for your answer. So what we're looking at here is our train at time 5 is traveling at 40 meters per minute, and then at time 8 is traveling at negative 120 meters per minute. And the question is, at some point between there, is it negative 100? Well, yes, to get from 40 to negative 120, you have to pass negative 100, but we need to make sure that we are on mathematically solid ground here. Okay, what I just described to you in layman's terms was the intermediate value theorem. The idea that if you go from point A to point B, you're going to attain every y value in between. That's the intermediate value theorem. But to use the intermediate value theorem, one thing has to be true. Your function has to be continuous. And that needs to be said in the problem. Did they tell me in this problem that the function v sub at is continuous? And the answer is kind of. What did they actually tell me? They tell me it's differentiable. Is that the same thing? Well, it's not the same thing, but to be differentiable, you have to be continuous. Okay? But we have to say that. So I'm going to give myself some space to write here. On part B, I'm going to say because v sub a of t is differentiable, it must be continuous. Okay. I have to do that. I have to say that much because I'm about to apply the intermediate value theorem. And if you apply the intermediate value theorem without stating your condition, then you're not on solid ground mathematically. So I'm going to make a note here that v sub a of 5 is 40. V sub a of 8 is negative 120. And 40 is bigger than negative 100 is bigger than negative 120. So by the intermediate value theorem, let's use the language from the problem here. Train A's velocity is negative 100 meters per minute at some time. Must be negative 100 meters per minute at some time between 5 and 8. So that's the real thing with these intermediate value theorem problems, that conceptually, I think a lot of people can look at the table and they know the answer is yes, but it's how do you get the points for that? And knowing that you have to take the fact that it's differentiable and then say that it's continuous can be a little bit tricky for some people. So we just want to make sure we've covered all of our bases there. Part C. At time 2, train A's position is 300 meters east of origin station, and the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time 12. Use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at time 12. Okay, so they said involving an integral, so I'm going to start my thinking there. I know that if I integrate from 2 to 12, that will give me the displacement from time 2 to time 12. And we know that this train is moving to the east, so in this case, displacement and total distance would be the same thing. And so if we want the total distance from the station, we're going to start with the 300 meters it already had traveled and add to that the distance it travels from 2 to 12. And so the value of this integral, we cannot know. We don't have a function to integrate. Instead, we have this table. So we're told use a trapezoid sum to approximate that integral. So let me start piecing this together here. For part C, we're going to have 300 plus the integral from 2 to 12 of v sub a of t dt. But I'm going to approximate the area from 2 to 12 using these three trapezoids. I have a trapezoid with a base of 3, a trapezoid with a base of 3, and a trapezoid with a base of 4. Okay, I'm going to preach don't do more work than you have to here. Okay, this is going to be 300 plus this trapezoid approximation. I'm not going to get cute. I'm just going to write all three trapezoid areas independently. So I've got the first trapezoid, 1/2 times 3 times 100 plus 40 plus 1/2 times 3 times 40 minus 120 plus 1/2 times 4 times negative 120 plus negative 150. So that is a trapezoid approximation of the area under the curve. Part C asked me approximate the position of the train. So the position of the train is 300 plus that meters. And leave it. What's the point? There is no good that can come from me trying to simplify this. I certainly could, but it will not help me. Okay, I have reduced this problem to basic arithmetic, addition, subtraction, multiplication, division. I can leave, and I will. Part B. Clean up a little bit here. Part D. Second train B, travels north from origin station. At time t, the velocity of train B is given by v sub b of t, and at time t equal 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equal 2. So what I have here is a situation where train A is traveling this way, train B is traveling that way, and the distance between them, which I will call C, is growing over time. I've been asked, find the rate at which the distance between A and B is changing at time 2. So your intuition hopefully tells you that this is a related rate problem. It certainly is. A, the distance train A is moving, has a certain rate. B, the distance train B is moving, has a certain rate. And those two, the relationship between those two rates affects the rate at which their distance between them is growing. So looking at my nice little illustration that I drew here, I can bet that Pythagorean theorem is going to come into play. So let's come down here where I've got a little bit of space and say if a squared plus b squared equals c squared, then I can take the derivative of this with respect to t and say 2a dA dt plus 2b dB dt equals 2c dC dt. Okay? And at this point, I want to start plugging in everything that I know. It says right here at time 2, the train is 400 meters north of the station. So at this moment of interest, B has traveled 400 meters north. I also know from question C, or from part C, that at time 2, train A had traveled 300 meters east. So at that same time, A is 300. How fast is train A moving at that time? Well, let's come up here. At time 2, train A is moving at 100 meters per minute. So, how fast is train B moving at that moment? Well, they gave me an equation right here, V sub B of t. So what is V sub B of 2? That would be negative 5 times 4 plus 60 times 2 plus 25. That's negative 20 plus 120 plus 25. The negative 20 and the 25 just make 5. So the speed of train B is 125. How fast is the distance between them changing? That's the thing I don't know. That's what I'm hoping to solve for, which means I need a value for C, which again, we're going to think about our Pythagorean theorem. If train A's distance is 300 and train B's distance is 400, Pythagorean theorem and Pythagorean triples tells me that at that particular moment, the distance between them is 500 meters. So 500 can be plugged in right there. Put it all together, and by put it all together, I mean get dc dt by itself. And this is what I have. I have 2 times 300 times 100 plus 2 times 400 times 125 divided by 2 times 500 whatever that happens to be. Let's pick a name for it. How about S? At time 2 minutes, again, let's use the distance, let's use the language from the problem. The rate at which the distance between train A and B is changing. So at time 2, the rate at which the distance between trains A and B is changing. Is S meters per minute. Okay, and S, I've just named that quantity right there that I didn't know, which is fine. You're allowed to do that. I also could have just copied that big fraction if I wanted to. Let's see, my notes here says that simplifies to 160 meters per minute. Okay. Number 5, this was an AB only problem. Average was 3.62. Again, we see what looks to be a sign chart here. Let's see what we've got. Number 5 says the twice differentiable functions f and g are defined for all real numbers x. Values of f, f prime, g, and g prime for various values of x are given in the table above. A, find the x coordinate of each relative minimum of f on the interval -2 to 3. Justify your answers. Okay, so when they say relative minimum, I know a relative minimum occurs when the derivative changes from negative to positive. So looking at my table here, looking at f prime and g prime, is there a moment where this graph changes from negative to positive? I see it happening right here for f prime, and I don't see it happening for, the question was only about f, so g prime doesn't matter. So to answer part A, I'll say f has a relative min at x equals 1 because f prime of x changes from negative to positive. There. Part B. Explain why. There must be a value c from -1 to 1 such that f double prime of c is 0. So, we have these existence theorems, the two biggest ones being the intermediate value theorem and the mean value theorem. And so whenever I see a question say, why must this value exist, my brain goes to those two theorems. I would like to use the intermediate value theorem because it requires less work generally, but I don't have any information about f double prime here, so that's not going to fly. To use the mean value theorem, basically what I'm saying is that between -1 and 1, if the slope is 0, which the slope of f prime is 0 because the y value doesn't change. So because the slope of f prime is 0 from -1 to 1, then there must be a value in between where the derivative equals 0. Now, that's only true if conditions are met. We talked about this with the intermediate value theorem earlier. To use the mean value theorem, your function has to be two things, continuous and differentiable. How do I know that's true? They told me in the problem that these functions are twice differentiable, which means f prime has to be differentiable, and if it's differentiable, it has to be continuous. So I know the answer is yes. I know the reason is mean value theorem, but to get full credit, I need to show my work correctly here. So I'm going to be a little bit careful. I'm going to start by saying that because f is twice differentiable, that implies that f prime is continuous and differentiable. So now that that's out of the way, I'm going to say by mean value theorem, there exists a c between -1 and 1 such that f double prime of c equals f prime of 1 minus f prime of -1 over 1 minus -1. The mean value theorem basically says at some point in your interval, the derivative at a point will equal the slope between your two endpoints. And so f double prime of c equals 0 minus 0 over 2 equals 0. That's what we want to see. By the mean value theorem, there must be a value of c such that f double prime of c has to equal 0. Part C, the function h is defined by h of x equals the natural log of f of x. Again, I'm seeing layers here. I'm thinking chain rule. Find h prime of 3. Show the computations that lead to your answer. So h prime of x equals, I'm looking at this function h of x up here. And to take its derivative, I'm going to apply the chain rule, which means I'm going to start with the outside layer. Okay, the derivative of natural log is 1 over whatever's inside. So 1 over f of x times the derivative of the inside function. The derivative of f of x would be f prime of x. So this is what I'm looking at. H prime is f prime over f. And I'm asked to find h prime of 3. So h prime of 3 is f prime of 3 divided by f of 3. How am I going to get these values? I hope they're up in the table. F prime of 3 is 1/2. F of 3 is 7. This equals 1/2 divided by 7. which you could simplify to 1/14th, but you don't have to. And finally, part D. Evaluate the integral from -2 to 3 of f prime of g of x times g prime of x dx. At first glance, this looks kind of gross. This is a little bit alphabet soupy. There's lots of letters here. But what I tell my students is if an integral looks hard, the first thing you should ask yourself is this a u sub? And it turns out it is. This is a u sub where if I make my u g of x, then my du would be g prime of x dx, which just so happens I have right there. So on part D, I've got this definite integral. If I'm doing a u sub, I might as well change the bound since I'm here, right? So -2 and 3, if I plug them in for x right there, g of -2 is -1, and g of 3 is 1. So there's my new bounds, and this substituted integral becomes the integral from -1 to 1 of f of u d, f prime of u du. And so the way definite integrals works is you take the antiderivative, plug in the top and bottom bounds, and subtract. The antiderivative of f prime is just f. So this is f of 1 minus f of -1. Again, what are these values? Go back to the table. F of 1 is 2, f of -1 is 8. 2 minus 8 is -6. So when you see those hard-looking integrals, those alphabet soupy integrals like this, then you're going to try and use a u substitution. Okay? Or if you're in Calc BC, it could be an indication that it's integration by parts. So that's what I think about when I see that, and it turns out if you do choose the right u, it simplifies down nice and easy. Okay. Number 6. This was again an AB only problem with an average of almost 4 out of 9 points. It says, consider the differential equation dy dx equals 3 minus y times cosine x. Let y equal f of x be the particular solution to the differential equation with initial condition f of 0 equals 1. The function f is defined for all real numbers. A portion of the slope field, part A, a portion of the slope field for the differential equation is given below. Sketch the solution curve through the point 0, 1. So quickly, I'm going to take a look at this graph and make sure I understand the scale of it. 0, 1 is right here. Choose a brighter color right here. And these slope field problems are not the most stringent. You just want to draw a curve in that sort of follows the flow of the slope field. I can see that slopes right here are sort of moving up, and then they're flattening out, and then they are moving back down. And then moving to the left, I have decreasing slopes that are flattening out and turning back upwards. Okay, that mostly fits the slope field. That is certainly good enough for drawing that in. B, write the equation for the line tangent to the solution curve in part A at the point 0, 1. Use the equation to approximate f of 0.2. So what they're asking you to do here is linear approximation. If you have the formula for linear approximation memorized and you want to do it in one quick step, that's great. If not, you can find the equation of the tangent line and then plug in 0.2. Both are fine. For me, I'm going to do part B right here. F of 0.2 is approximately f of 0 plus f prime of 0 times 0.2 minus 0. That's the all-in-one process for linear approximation. So do I know these values? F of 0 is 1. F prime of 0, well, how do I know f prime of 0? They gave me a differential equation up here, and I have a 0.2 plug into it. So let's take a step aside here and say, what is dy dx at the point 0, 1? That would be 3 minus 1 times cosine of 0. 3 minus 1 is 2, times 1 is 2. And 0.2 minus 0 is 0.2. So f of 0.2 is approximately 1 plus 2 times 0.2. 1 plus 0.4 is 1.4. And part C. Okay, these differential equation problems, when they gave me a differential equation up here, one of the things that I did notice is that it is separable. And because it is a separable differential equation, I know that I might be asked to separate it and actually solve it. And that is what part C is asking me to do. Find y equal f of x, the particular solution to this differential equation with initial condition f of 0 equals 1. Notice the verbiage here. Y equals f of x means they want my final answer to have y by itself. So when it comes to separable differential equations, you want to get all your y's on the left, all your x's on the right, integrate both sides, plug in your initial condition to solve for plus c. And that's what I'm going to do. 3 minus y times cosine of x. dy dx equals 3 minus y cosine of x. So step 1, separate. I'm going to divide both sides by this 3 minus y. I'm going to multiply both sides by this dx. That's going to look like this. 1 over 3 minus y dy equals cosine x dx. Then I'm going to integrate both sides. Keeping in mind that on the left-hand side, that's going to be a u sub. It's one that you can do in your head. It's a simple u sub, but the derivative of 3 minus y is -1, so just be on the lookout for that. On the left-hand side, I'm going to have negative natural log absolute value 3 minus y. On the right-hand side, the antiderivative of cosine x is sine x plus c. Remember, you only need 1 plus c, because if you had 2 plus c's, you would combine them, you get another constant altogether. We're still going to call it plus c. So what I need to do two things. I need to solve for plus c, and then I need to get y by itself. So I'll go ahead and solve for plus c using my initial condition that I can plug in 0 for x and 1 for y. So negative natural log of 3 minus 1 equals sine of 0 plus c. Sine of 0 is just 0. So c equals negative natural log of 2. So that brings me to here. Negative natural log absolute value 3 minus y equals sine of x minus natural log of 2. Getting y by itself can be tricky until you have some practice with this. Let's start by getting the natural log by itself. To get the natural log by itself, I'm going to multiply this entire equation by -1. So now sine x is negative, natural log 2 is positive. Then, because the entire left-hand side of my equation is a natural log, I can make it a power of e, make both sides a power of e to simplify, leaving me with 3 minus y on the left, and e to the natural log of 2 minus sine x on the right. This is something that can be simplified, but I'm going to save that for the end. To get y by itself, I'm going to basically add y to this side and subtract all of this over there, trying to keep it simple. So y equals 3 minus e to the natural log of 2 minus sine x. That is y by itself. That is certainly a boxable and runnable answer. But I do want to point out e to the natural log of 2 is just 2. So I would write it like this. 3 minus 2e to the negative sine x. Yeah. Either one of those would be okay. This top example, the top answer I put is fine for free response, but you would never see something like that on a multiple choice. The bottom one, it would be like the multiple choice approved answer, and that's what College Board considers to be the perfect answer. So keep in mind with these separable differential equations that you don't have to get the perfect right answer to get all the points. You're accumulating points as you go. You get points for separating, you get points for correct antiderivatives, you get points for remembering plus c, you get points for solving for plus c, and you get points for getting y by itself. So if you get everything right and don't get y by itself, it's not the end of the world. As a matter of fact, if you did all of part C and didn't get y by itself, you would still beat the national average on this problem if you skipped A and B altogether. And so that's it for the AB problems. That is all 6 AB problems from that year. 3 of the problems are different for the BC exam. So I'm going to move on and start talking about the BC problems. If you are an AB student, you can hang around if you want to see some cool stuff. Otherwise, your job here is done. Looking at now at the BC specific problems, the first one that was different was number 2. The average on this was about 4 points. It was, as you can quickly see, a polar problem. I have a question in chat. Why does the natural log on the left disappear, but the one on the right doesn't? The one on the right does. It just depends on whether or not you choose to simplify. It disappears when e to the natural log 2 becomes this 2 right here. The reason why, because it was paired, the natural log was paired with the sine x, so it all had to go into the exponent together. But technically it does cancel out eventually. Thank you for the question. Okay, here we go. Polar problem. The graphs of the polar curves r equal 3. So I'm going to do my best to label these. R equal 3 would be this semicircle right here. And r equals 3 minus 2 sine 2 theta would be this graph. Are shown in the figure above from 0 to pi. Let R be the shaded region that is inside R equal 3 and inside 3 minus 2 sine 2 theta. Find the area of R. So when it comes to polar graphs specifically, these intersection points are going to be important. I can see that these two graphs are intersecting right here. You can find that intersection point, first of all, by noticing that it is straight up the y-axis, and so we know which angle is straight up the y-axis. But also, you could just set these equal to each other. 3 equals 3 minus 2 sine 2 theta. Subtract 3 on both sides. 0 equals negative 2 sine 2 theta. Divide both sides by negative 2. 0 equals sine of 2 theta. Uh-oh. There we go. And so the question is, what do I plug in for theta so that sine of that is 0? We know that sine of let's pause for one moment here before I say something silly. Because I want this to be pi over 2. Yeah. So if I plug in pi over 2 times 2 is pi, sine of pi is 0. So theta equals pi over 2. These also intersect, I should have mentioned, over here, that is at theta equals 0. So this equation has two solutions, pi over 2 and 0, because of those two intersection points. And if I kept going, they intersect again over here, but I'm not interested in that intersection point right now. So for part A, find the area of R. So I'm trying to find the area inside the shaded region. Remember that we accumulate area using our magic windshield wiper. And so when we start windshield wiping this area, the curve that we are radiating out to, at least initially, is the blue curve. So that area, remember polar area is 1/2 integral r squared d theta. So this is going to be 1/2 integral from 0 to pi over 2 of 3 minus 2 sine 2 theta squared. That's the first part of the area. Then as I finish it out, the rest of this area, I'm radiating out to the red curve, which is the circle. So I'm going to add to that 1/2 integral pi over 2 to pi of 3 squared d theta. And thankfully, this is a calculator active problem. So I can come to my calculator here and plug all of this in and get 9.708 as the value of these integrals, 9.708. Remember, we accumulate area radially with polar graphs. We accumulate area radially. So I call that the magic windshield wiper, where as you rotate around, you gain more and more area. Part B, for the curve r equals 3 minus 2 sine 2 theta, find the value of dx d theta at theta equals pi over 6. So up here, where I've got some space, I want to make a quick note. We know x equals r cosine theta. That is one of our conversion formula for polar graphs. So in this case, r is 3 minus 2 sine 2 theta. So that's the value of x. So when they say find dx d theta, we're taking the derivative of this, 3 minus 2 sine 2 theta times cosine theta with respect to theta. And to do that, that's going to require the product rule. So let me copy this. So when I take the derivative of this using the product rule, the derivative of the first term would be 0 minus 2 cosine 2 theta times 2. So minus 4 cosine 2 theta times cosine theta. So that's f prime g plus f times the derivative of g. So the derivative of cosine is negative sine theta. And they want to know, they being the AP exam, find the value of dx d theta at theta equals pi over 6. So dx d theta evaluated at pi over 6 is going to be negative 4 cosine of 2 times pi over 6, so pi over 3, times cosine of pi over 6 plus 3 minus 2 sine of pi over 3 times negative sine of pi over 6. Almost ran out of room there. You can box and run this. It kind of makes me a little bit uncomfortable. I'm still not okay leaving unsimplified trig expressions. So I would probably take it a step further. Negative 4 times 1/2 times square root of 3 over 2 plus 3 minus 2 times square root of 3 over 2, so square root of 3 times negative 1/2. I probably would leave that just as is. You can certainly simplify it. Oh, and this was a calculator active problem. I guess I got carried away a little bit there. So we could have simply put this in our calculator and then told our calculator to take the derivative at pi over 6, which would have been negative 2.366. I'm still in non-calculator state of mind. Part C, the distance between the two curves changes from 0 to pi over 2. So let me clean up my picture here a little bit. So the distance between the two curves is changing, we can see from 0 to pi over 2, we'll call this d. Find the rate at which the distance between the two curves is changing with respect to theta when theta is pi over 3. So if d is the distance between these two curves, that distance is measured outside minus inside. So d, the distance between these two curves, is 3 minus 2 sine 2 theta, which we can see here those 3's are going to cancel out, so that's just 2 sine 2 theta. And so I'm simply being asked what is the derivative of that. If the distance between them is 2 sine 2 theta, then the derivative, d prime, would be 4 cosine 4 theta. And that rate at theta equal pi over 3, oh, I'm sorry, I put a 4 where I meant to put a 2 right here. 4 cosine 2 theta. D prime of pi over 3 would be 4 cosine of 2 pi over 3. Cosine 2 pi over 3 is negative 1/2. 4 times negative 1/2 is negative 2. And last one, a particle is moving along the curve 3 minus 2 sine 2 theta so that d theta dt equals 3 for all times t greater than 0. Find the value of dr dt at theta equals pi over 6. So here's what I know. I know that r equals 3 minus 2 sine of 2 theta. But now we are being asked to take the derivative of this not with respect to theta, but with respect to t. So this is a bit of an implicit derivative meets polar graphs problem, where dr dt equals 0 minus 2 cosine 2 theta times 2 d theta dt. I'm taking the derivative with respect to t instead of theta. And so here's where I'm at. I've got negative 4 cosine 2 theta d theta dt. And the question I'm being asked is, if d theta dt is always 3, so I can plug in a 3 for this, then find the value of dr dt at theta equals pi over 6. So dr dt when theta is pi over 6 is negative 4 cosine of pi over 3 times 3. That's negative 12 times 1/2 is negative 6. Okay. The other problem that was different on the BC exam was number 5. This had an average of 4.5 points. It says let R be the shaded region bounded by the graph of y equal x e to the x squared. So that's going to be this exponential graph here. The line y equals negative 2x, that's going to be this straight line right here. And the vertical line x equals 1, this vertical line here, as shown in the figure above. A, find the area of R. So this is an area between two curves graph. I already know the bounds are 0 and 1, but this is a non-calculator problem, so I guess therein lies the problem. So for part A, this area is the integral from 0 to 1 of top minus bottom, the integral from 0 to 1 of x e to the x squared minus negative 2x, so plus 2x dx. At this point, you could work this integral out however you want to. There's going to be a u sub involved. For me personally, I would split this into two integrals. I would treat this as the integral from 0 to 1 of x e to the x squared plus the integral from 0 to 1 of 2x. The reason why I like doing that is because now the integral that needs to be solved with u substitution, x e to the x squared, is by itself, and 2x, a more simple problem, is by itself. So when I apply u substitution here, if I say u is x squared, du would be 2x dx, so I need 1/2 du equals x dx, and my bounds 0 and 1. 0 squared is 0, 1 squared is 1, so this is the integral 1/2 integral 0 to 1 of e to the u du. That's 1/2 e to the u from 0 to 1, which is 1/2 e to the first power minus e to the 0 power, plus the antiderivative of 2x is x squared. Plug in 1, plug in 0, and you get 1. So what I've got here is 1/2 e minus 1 plus 1. Which again, you could combine like terms, make it e over 2 plus 1/2 if you wanted to. B, write but do not evaluate. An integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals -2. Whew, okay. So my first question when I look at this is, what is this point down here on the bottom right-hand corner? That's the intersection of -2x and x equals 1, and so that point is 1, -2. So that is my axis of rotation. Write but do not evaluate, thank goodness, an integral that gives the volume of the solid when r is rotated. So what I need to know is, this is going to be a washer problem. I've got this empty space here that I'm traveling through, so this is a washer volume. So I need my big R and little r. Big R would be this distance right here. Little r would be this distance right here. Finding these distances with top minus bottom is the most consistent way. Big R is the distance between x e to the x squared and -2. So that's x e to the x squared minus -2. Little r is the distance between -2x and -2. -2x minus -2. There's your values for big R and little r, and now we're going to piece it all together. This is a revolution problem. Don't forget the pi. Excuse me. So I've got pi times the integral from 0 to 1 of big R squared x e to the x squared plus 2 squared minus little r squared -2x plus 2 squared dx. And then finally, write but do not evaluate an expression involving one or more integrals that gives the perimeter of R. I love this problem. Perimeter means we're adding up all three sides. And we've got sort of different strategies for all of them. We'll start with the hardest one, and that is the length of this side. We're going to need to use our formula for arc length there. So remember that arc length is the integral of the square root of 1 plus dy dx squared. So the integral from 0 to 1 of the square root of 1 plus the derivative of x e to the x squared. So I need to pause here, go somewhere else, and find the derivative of x e to the x squared. That's going to require the product and the chain rule. I've got f prime g e to the x squared plus f g prime x times e to the x squared times 2x. So that's e to the x squared plus 2x squared e to the x squared squared dx. That is the integral of the square root of 1 plus dy dx squared. That's the first part. So we'll make that blue. Plus We'll do this one next. This distance, this red line, this is a straight line between 2 points. You can use an integral if you really want to, but I think the distance formula or even Pythagorean theorem would work well for that. Basically what we have is a right triangle where you go over 1 and down 2. So if this is 1 and this is 2, then the hypotenuse would be 1 squared plus 2 squared square rooted. So that's the square root of 5. Plus this distance right here. Okay, that is a straight line. We know that the distance, let's break it up into 2 parts. You got 2, that's how far it is to the x-axis, because we know that point is 1 comma negative 2. And then the distance from the x-axis to that top point is what happens when you plug 1 into x e to the x squared. You get 1 e to the 1. So that's e. So that total distance is 2 plus e. So there's your perimeter. We've got this arc length integral plus square root of 5, which we got from Pythagorean theorem, plus 2 plus e, which we got from piecing together the bottom part and the top part of that vertical line. Okay, and then our last one. Last one, number 6. BC number 6 is almost always a Taylor series problem. This one is no exception. The average was 3 points. The Taylor series for a function f about x equals 1 is given by the sum from 1 to infinity, negative 1 to the n plus 1 times 2 to the n over n times x minus 1 to the n, and converges to f of x for x minus 1 an absolute value less than r, where r is the radius of convergence of the Taylor series. So let's pause for a second and recall the center here is definitely 1. A says find the value of r. So we're basically being asked to find the interval of convergence here. We're being asked to find r, not necessarily whether or not the endpoints converge, which will save us some time. But ultimately, we're going to solve this the way that we usually do interval of convergence, which is with the ratio test. So for part A, I'm going to say the limit as n goes to infinity of the absolute value of the n plus first term, that would be negative 1 to the n plus 2 times 2 to the n plus 1 times x minus 1 to the n plus 1 over n plus 1 divided by the nth term. We're going to flip and multiply. So times n over negative 1 to the n plus 1, 2 to the n, x minus 1 to the n. And with the ratio test, we expect lots of cancellation. First of all, the alternating parts, they go away. Absolute value takes care of them. Where do I have more 2's? I have more 2's on top. I have n plus 1 2's on top and n 2's on the bottom. So I'm left with a 2 in the numerator. I'm left with an x minus 1 in the numerator. Times n over n plus 1. So as n goes to infinity, we've got the same relative growth rate. On top, we have 2x as a coefficient for n. On bottom, we have 1 as a coefficient for n. So this is equal to the absolute value of 2x, which has to be less than 1. So if the absolute value of 2x is going to be less than 1, that means negative 1 is less than 2x is less than 1. Divide everything by 2 to get this interval of convergence. Now, we haven't checked the endpoints yet, but we don't have to because we knew this was going to be centered at 1. Pause for one moment here. I see. Sorry. Make a slight correction here. When my answer wasn't centered at 1, I knew something had happened. This coefficient was 2x minus 2. Add 2 to everything. That's much better. That is a interval that is centered at 1 and has a radius of 1/2, because from 1 to 1/2 or from 1 to 3/2 is 1/2. So r equals 1/2. That's the radius of convergence. B. Find the first 3 non-zero terms and the general term of the Taylor series for f prime, the derivative of f. So I'll need to make a little room for myself here. Okay. Let's start by we can find the first probably 4 terms of f and then take the derivative of the first 4 terms, or we can take the derivative of the general term and then write out the first few terms. I'm partial to that strategy. So f prime of x is the sum from 1 to infinity of -1 to the n plus 1 times 2 to the n over n times n x minus 1 to the n minus 1. Okay, all that we're doing, we're basically using the power rule. The exponent n comes down and then decreases by 1. The n's are going to cancel here, which is nice. So I have the sum from 1 to infinity of -1 to the n plus 1 times 2 to the n times x minus 1 to the n minus 1. So when I want to find the first 3 non-zero terms, I'm going to start by plugging in 1 for n. So that's going to be -1 to the second power, so 2 times x minus 1 to the 0 power, plus, actually minus because it's alternating, minus 2 to the second power, so 4 x minus 1 to the first power, plus 2 to the third power is 8 times x minus 1 squared. So 2 minus 4 times x minus 1 plus 8 times x minus 1 squared minus ... plus -1 to the n plus 1, 2 to the n, x minus 1 to the n minus 1. There's your general term. So find the first 3 terms in the general term of f prime. We've now done that. And the last part, the Taylor series for f prime about x equals 1, found in part B, is a geometric series. Find the function f prime to which the series converges for x minus 1 less than r. Use this function to determine f for x minus 1 less than r. So the question is, how can we take the series that we have and rewrite it as a geometric series? If I have the sum from 1 to infinity of -1 to the n plus 1, let's make everything to the nth power. So I got -1 times -1 to the n times 2 to the n times x minus 1 to the n over x minus 1. So what that allows me to do is rewrite this as -1 over x minus 1 times -2 times x minus 1 to the n. Now it looks geometric. I have something times something to the nth power, so I can see that my common ratio, r, is -2 times x minus 1. And so we know that a geometric series converges. If it converges to a sub 1 over 1 minus r. So this converges to a sub 1. Well, we already know the first term from part B is 2. So 2 over 1 minus -2 times x minus 1. Which is 2 over 2x minus 2 plus 1, 2x minus 1. So it's important to remember what we just found is f prime of x. Okay, we took the derivative in part B. We took that derivative series, expressed it as a geometric series, and rewrote it as a function here. To find f prime, they said use this function to determine f. So the last thing I need to do is take the antiderivative of this, the antiderivative of 2 over 2x minus 1. We'll just treat it as a u sub. U is 2x minus 1, du is 2x or 2dx. So I've got the natural log of the absolute value of 2x minus 1 plus c as my f of x. And because I have an initial condition, because I know that when I plug in, let me find it, when I plug in 1, I should get 0. So natural log of 2 minus 1 plus c is 0. Natural log of 1 is 0. So c is 0. So f of x is the natural log absolute value 2x minus 1. And that is it. That is all 9 free response problems from 2014. I'd like to do this semi-regularly from now until the AP exam, just as a means of review and also practice for myself to learn how to work these streams and stay fresh on the content. So I hope you learned something. I hope you enjoyed it. I hope you tune in next time. Thanks, everyone. Bye.